Okay, today in class we did a little bit more challenging problems, and I didn't know what else to call it, so I called it more challenging acid-base problems. They're not really that hard, they're just a little bit worded different, so I just wanted to make sure you understood how to work these. Our first example, we're trying to find the pH of a solution that is mixing two acids together, and there are different volumes of our acid. We're adding 25 milliliters of a 0.02 molar hydrochloric acid, which is a strong acid, and then 30 milliliters of a 0.01 molar hydroiodic acid, which is also a strong acid. So the two acids are not going to chemically react with one another, so I wouldn't write a reaction with hydrochloric acid plus hydroiodic acid. So there must be something they're sharing in common, and they both have the hydrogen ion, which is what we need to find pH. So your first step, because you can't just add molarities together, because when you add the volumes together, the molarity is going to change, because molarity is moles divided by the total volume. So you're going to convert both of these to the mole. So I'm going to convert by multiplying your liters, so 0.025 liters. I'm going to multiply it by the molarity. And this is the hydrochloric acid we're doing first. And that's going to get us a moles of 0.0005. And that's our moles of HCl. But if you think about it, HCl is going to do what? It's going to break apart in the water. And so it's going to give me hydrogen ions, and it's going to give me chloride ions. So this is the amount of moles of the hydrogen, and it's also the amount of moles of the chloride. What I really care about is those hydrogen ions. The chlorides are just going to be spectators. So even though it's HCl, the Cl is really a spectator because this is a strong acid, and I really only care about the hydrogen. I'm going to repeat, and I'm going to do the same thing, change my volumes to liters, multiply it by the molarity. This is hydroiodic, which has hydrogen ions and iodide ions. The iodine, again, is going to be a spectator. So really, again, this is just a spectator. I'm really caring about the hydrogen ions. So once those ions get there in the solution, they're going to give us a total number of hydrogen ions. So we simply could add those together. So I add those together, and we have a total 0.008 moles of the hydrogen. Technically, we've got this amount of the chloride and this amount of the iodide. Again, they're spectators. Well, to find the pH is the negative log of the hydrogen ion, but it's not in moles. The formula is pH is a negative log, and the brackets means molarity. So I have to have this in molarity. Well, that's moles. So I got to take the pH of that in molarity, which is your moles, 0.0008 moles of hydrogen, divided by the total volume. The total volume is here. You're going to be pouring those two containers together. So you've got 30 milliliters and 25 milliliters. So you have 55 total milliliters, which is going to give you a total volume of 0.055 liters. Now you could do that separate, or you could do it all in this. What I mean separate is you can actually calculate the molarity and then take the negative log of that, or you could just write it like that. Either way you want to do it. And then you'll find the pH of the two acids put together is a 1.84. So we would only do this for strong acids, because weak acids you start getting a lot more complicated because you have those Rice equations, etc. Okay, our next one is even a little bit easier. You've got, calculate the pH of, if you have 5 milliliters of a 0.1 molar hydrochloric acid. If I just took the negative log of that, you would find that the pH of the original solution is 1. Negative log of 0.1 is 1. But I'm going to dilute it down, so I'm going to put some water in it, and I'm going to see the pH actually be greater than 1, because I'm going to be putting water into it, so the pH is going to rise. It's going to become more basic, or should I say less acidic. This is essentially a dilution problem. So we've done this formula before, the initial molarity, initial volume, and the final molarity, final volume. So I need to find the new molarity once I dilute this thing down. So the initial molarity was a 0.1 molar hydrochloric acid. The initial volume, because this is a proportion, you can leave it in milliliters. You can change it to liters if you want, but we can leave it in milliliters since milliliters are going to be on the both on the same. They're going to cancel each other out, is what I'm trying to say, since the same unit is on both sides. So we're looking for the final, and it doesn't say that we added 200, but we got to a total of 200. So that's my final volume. I'm going to multiply these and divide by the 200, and I would find that we have a final molarity of 0.0025, and that is our molarity of our HCl. And of course, that's a strong acid that's going to break apart 100%, and since it breaks apart 100%, I could simply take the negative log of 0.0025 to find the pH, because strong acids are super easy to find the pH of. And so we get a pH of 2.60. So before I diluted it, it had a pH of 1. I added 195 milliliters of water, and we have elevated the pH to 2.6. Not hard, just a dilution problem. All right, our third problem that we did in class was something called a polyprotic acid. Poly means many, protic means hydrogen. Polyprotic means it has more than one hydrogen to come off. So this could mean you could have a double rice or a triple rice. What I'm going to do on the video is a double rice, and I'm going to give a double rice on your quiz, and you'll have a double rice on your test, and then I'm going to give a triple rice for a bonus to see anyone that would want to take that challenge. A double rice meaning it has more than one hydrogen, for example, carbonic acid, H2CO3. There are two hydrogens, but they don't come off. One, they don't come off completely, and they don't come off both at the same time. They're not strong, so they come off one at a time. A triple rice would be like phosphoric acid. It has three hydrogens. So we're going to do the double. So we start out with our initial rice, and it is carbonic acid. Draw the double arrow. Excuse me. And one hydrogen comes off at a time, so we're going to take one hydrogen off. When I do this, this does not have a charge right now, and when you take off a positive one, you end up getting this hydrogen carbonate or bicarbonate ion there. So now it has a negative one. We're going to start out with 0.0037 molar. This is 0, 0. This is going to be minus X. We're going to add X, add X. We get X, X. So it just looks like a normal pre-AP rice table is what it looks like. So then we're going to put the products over the reactants, so you end up getting X squared, or 0.0037 minus X. We're going to set that equal to something. If you'll notice, there's a Ka1 and a Ka2 because it has two hydrogens coming off. The Ka1 is for the first hydrogen. The Ka2 is for the second hydrogen. You can see that the number gets a lot smaller, meaning it's not real favorable for that second hydrogen to come off. It's not great favorable for the first hydrogen to come off. Now, as long as this is to the negative fifth or smaller, you can mark through your minus X here, and then you could cross multiply or send this over and take the square root. Or if you're just a solver fan, you can use a solver. So whichever you prefer, you need to find X. I do believe if you don't use solver, you get 3.99 times 10 to the negative fifth. Or if you decide you want to use solver, you get 3.97 times 10 to the negative fifth. Okay, so that is our concentration. So whichever number, that is your molarity. we can trace our x back up. Today in class, they wanted to use the solver. They kind of are solver fans, which is fine. So we use the 3.97. It really gets us the same answer in the end, so it really didn't matter one bit. Because this is to the negative fifth, so that's a really small number there. And if I take 0.0037 and I subtracted something to the negative fifth and I rounded back to 2 sig digs, it actually would round right back to that number. It's less than that 5% rule that we have talked about in class. Alright, well our problem is that there's more hydrogen to come off of this. So, and also it asks for the carbonate concentration. So that's not carbonate, that's bicarbonate or hydrogen carbonate. So I'm going to now start with this ion, that hydrogen carbonate, and do my second rise. So HCO3 minus 1. Now its hydrogen is going to come off. Not very well, but it's going to come off. Now, we usually put zeros under those, but if we go back up, I'm going to get this thing to move with me, there's some hydrogen here. So we've got a value here. So this is going to come down in our table, and this is going to be our initial for this guy. So we don't care about that guy because he's not in our new rise table. But this guy has a value. And like I say, we use this number in class, so I'm just going to work with that one. But you could do the 99. And nowhere up there did it mention the carbonate, so it's starting out at 0, which is good because if it starts out at 0, we know where we need to add the x to. So we're going to add the x here, we're going to add the x here, and we're going to subtract the x there. So we get 3.97 times 10 to the negative fifth minus x, and then 3.97 times 10 to the negative fifth plus x, and then we got 0 plus x. It's getting really pretty now. So now on the top we get 3.97 times 10 to the negative fifth plus x times x divided by 3.97 times 10 to the negative fifth minus x. And we're going to set this now equal to, whoops, where'd it go? Our Ka2, 5.6 times 10 to the negative 11th power. Well, a second ago, this was to the negative 7th, and I could mark through my minus x. This has now gotten a lot even smaller, so I can get rid of this minus x here. I can also get rid of this plus x. And now if you'll see the top and the bottom are the same, those are going to cancel, so our x magically equals our Ka2. Does that always happen? A good percentage of the time, depending on your K value. Now, if this had been like to the negative third or something, no, it wouldn't happen. But I don't think on any of the polyproducts it's any number like that. All right, so now there's my second X. If I follow this up, it's asking for the carbonate, and carbonate is X. So this is the answer to my carbonate ion. To find the pH, well, I need the negative log of my H+. Well, I had them in class to check this. If you'll notice, 3.97 times 10 to the negative fifth, and we're going to add x to it, and x was 5.6 times 10 to the negative 11th. If I add this number and that number together, look at the power difference. It's essentially the same number, but I had them do that and take the negative log of it to find that pH. And then I had them just take the negative log of the original number. And what we found out with those two different numbers, using the bottom equation, we got an answer that looked like this. Using the top and not the plus x, this part, not the bottom right, we got an answer that looked like this. Whoops, there's a 4. and I may have those mixed up, which one's which. But I wanted to prove a point that essentially, because we're going out two decimals, all the pH, the true pH, is oops, coming from the first hydrogen coming off. So most of the hydrogen ions are here, coming the first one. The second one barely comes off and barely gives us any hydrogen, affecting the pH just way out in the decimal, and it's not even lowering it hardly any at all. I mean, it's lowering it. That's definitely a lower number, but way on out. So a polyprotic, to find the pH, you definitely can just Bryce it once. But to get that second ion and to get full credit on your quiz, you're going to want to Rice it second just to kind of prove it. So that's all we did today, and then you can see your assignment is in the book, and then I gave this polyprotic one to do because I didn't like the ones in the book. So short little assignment in the book, and then there's polyprotic here. Notice this is to the negative second power, so you're going to have to use solver because it's not a small enough K to let us scratch through the X. So if you have any questions, please come see me.